All right, guys, one more video for today. So we're going to be looking at 3.1, 3.2, 3.3. These should all be relatively light compared to the last unit. So let's go ahead and jump right in with 3.1, specialist versus generalist species. So we're going to be building on some of the stuff that I mentioned briefly in the last unit. So here we've got two pictures. We've got a red panda with its cute little adorable face right there, and a raccoon. So evolutionarily, when we look at these two species, they're very closely related, but when we look at their role in the environment, they're extremely different from one another. So the red panda is going to be what we call a specialist species. So it's going to have a very specialized niche. So it doesn't really digest cellulose very well. So it's going to eat very large quantities of bamboo to meet its caloric needs in a day. Whereas something like a raccoon is going to be able to eat a lot of different food sources, anything from plants, mushrooms, eggs of birds, even small animals. So it's going to be what we call a generalist. So today we're going to identify the difference between those two. And then for our FRQ, we're going to explain environmental concepts and processes. So with our specialists, you can see on our graph here, their um, niche is very narrow. It's very small. So it has a smaller range of ecological tolerance. So that means that they don't have a wide variety of things that they can adapt to or that they can survive with. So this makes them more prone to extinction. They're going to have very specific food requirements. So in this example, the panda, even though it's a very large animal, is going to eat primarily just bamboo. They're less able to adapt to new environments with the digestive system that a panda has. If we were to take it and drop it in a tropical rainforest or even a temperate rainforest, it would not be able to survive. Whereas our generalist, when you look at their niche over here, it's very broad. So they have a larger range of tolerance. They can survive a lot of different environmental conditions. So this makes them less prone to extinction, but it does make them more prone to be considered an invasive species. They have very broad food requirements. So if one type of their food is low, they can switch to another type, and they're very adaptable to their environment. So when we look at some characteristics here, we can see that our specialists, things like our koala and our panda, they have a very narrow niche. They're less adaptable because of the specialized needs that they have. They're more likely to become extinct because they can only use a specific set of resources, which makes them easily affected by changing conditions, but they do have an advantage when they live in ecosystems where conditions are more constant. You could essentially say that specialists are picky. And then generalists, over here we've got the rat and the raccoon, and they're essentially opposite of our specialists. They have a very broad niche, they're adaptable, they're less likely to become extinct because they can handle changing environments, they use a wide variety of resources, and they have a very high range tolerance. So they can survive, in a wide variety of, let's say, temperatures, for example. And so they have an advantage when they live in ecosystems with changing or unstable conditions. And that's all I have to say about those, okay? Very simple. So for your FRQ for this unit, I want you to identify. So just say it, just say one characteristic. This is a characteristic of a specialist species. Just state it. And then explain how that characteristic makes them more likely to go extinct than a generalist species. So that's where you're going to have to give a little bit more detail. All right, then jumping into 3.2. So with 3.2, we've got our K selected and R selected species, which we also talked about a little bit last unit. So for K selected, that's going to be things like our elephant here and its adorable little baby. And so they kind of take the quality over quantity approach when it comes to reproduction. So K selected and R selected are both reproductive strategies. They both work, they just work differently. So with our K selected species, we tend to see them living for a very long time, so they can devote more time to parenting, so they tend to have less offspring. With our R selected species, they go the quantity route. So they pass on their genes by having a lot of offspring at a time, because many of these organisms are only going to reproduce one time in their entire life. So they have to make it worth it. They have to really crank out those offspring. So our examples here would be the spiders. They can have hundreds of offspring at one time, and many spider species will essentially have their offspring and then leave. They have no parental care of those offspring, so they just essentially leave and hope that some make it to adulthood. So, as we look at our essential knowledge today, it looks like a long list, but it's not that bad, I promise. The first two here are essentially just the difference between K and R selected species. But we do have a new term in our third essential knowledge bullet down here, which is biotic potential, which essentially is just the maximum reproduction or reproductive rate of a population, and that tends to be much higher for R selected species than for K selected species. And then we also need to understand that, like a lot of things in life sciences, um, they're not uniquely one or the other. It's kind of a spectrum, and organisms are going to fall somewhere on that spectrum. So then our skill today, we actually are going to have two practice FRQs, but I think it's okay because 3.1 was so short. We're going to describe patterns or trends in data. So when we look at the differences between these two, they're essentially opposites of each other. And even though this is a capital R here, typically it is represented by a lowercase r, which I actually think is helpful. I really truly don't know why this one is lowercase and this one is uppercase, but I'll explain why that makes sense to me in a little bit. So our K selected species, like I said, they go the quality route. So they're going to have fewer offspring, but they're going to have very heavy parental care. So they're going to protect those offspring. These are typically going to be organisms that reproduce many times in their life. Most mammals are going to be K selected species, and a lot of birds are also K selected species. These things tend to have a long lifespan, which means it takes longer for them to reach sexual maturity. So, because it takes them longer to reach sexual maturity, they don't have as high of a biotic potential, which means they have a slow population growth rate. So, if there's some kind of environmental change or some kind of invasive species, it's harder for them to rebound from that because it takes them so much longer to build up their population size because they have a few offspring at a time and they spend a lot of time raising that offspring. So when we look at our R selected, they take that quantity approach. So they have a lot of offspring, they have little to no care of their offspring, they may reproduce only once, so things like insects, fish, plants. Now, they tend to have, on average, a shorter lifespan. And so you can kind of see why I said this is a spectrum, because some of our plants, like our oak trees, our maple trees, can live incredibly long time, hundreds of years. So they would fall somewhere on the spectrum between R and K. But most things are going to have a shorter lifespan. They're going to reach their sexual maturity very quickly in life. So that means they're going to have very high biotic potential. They can produce a lot of offspring in their life since they reach sexual maturity so quickly, which means they're going to have very high population growth rates, which makes them more likely to be invasive since they can reproduce so quickly. They can have more and more and more and more of their offspring taking over that new environment. And they're also better suited for rapidly changing environmental conditions. So we can kind of look at K selected as being slow and steady. You kind of think of like the tortoise and the hare. And I don't mean this as a tortoises are one and hares are the other, because as you'll see, we're going to talk about hares next, and they're kind of in the middle of the spectrum. But K selected is kind of slow and steady like that tortoise, whereas R selected are much quicker at reproducing, like the hare was quicker in the race. Okay. So one reason I said that the K versus R made sense to me, being lowercase and uppercase, is because a lot of times our K selected species are going to be larger species. So that capital K makes sense to me. Whereas our R selected species tend to be a little bit smaller. So the lowercase r makes sense. So this is just a table that kind of summarizes their traits. And as you can see, they're essentially opposites. So our K selected are going to have long lives, while our R selected have short lives. Our K selected, it's going to take a long time for them to be able to reproduce, and our R selected are able to reproduce relatively young. K selected species are going to have very few reproductive events in their life. For example, an elephant is pregnant for almost 2 whole years, and then it typically takes them another 5 to 7 years until they'll produce another offspring. So they have a lot fewer reproductive events, even though they live long lives. Our selected species could have potentially many reproductive events depending on what the species is. When you think about things like rabbits, for example, or even rats, once they have their babies, they're able to reproduce again very quickly after that litter is born. Our K selected species are going to have very few offspring at a time, where our R selected will have a lot, and that's for a couple reasons. Number one is the size of offspring. The size of K selected offspring tend to be larger, and they're much smaller for R selected. Think about things like rats. When they're born, they're teeny tiny, okay? Super small. If you've ever seen the food I feed the snakes, for example, Eddie is a very small snake right now, so his mice that he eats are very tiny. If you've never seen Eddie's mice and you want to see what they look like, ask me. But they're very, very small. Okay. So parental care is going to be much more prevalent in our K selected, where it's absent in our R selected. So that is going to impact our population growth rate. So we're going to have much slower growth in our K selected than our R selected. Our population regulation for our K selected is going to be density dependent. So the more offspring there are currently alive and born in a population, the less offspring they will continue to have. Whereas with our R selected, it doesn't matter if a rat just had a litter of 8, 10, 12 pups, it's going to continue to reproduce. It's density independent. And when we look at our population dynamics, that makes our K selected species have a much more stable population size. It's going to kind of live near our carrying capacity. Whereas with the R selected species, it's going to be highly variable. We're going to have big kind of peaks and dips in that population size. So this is what I mean when I say it's a spectrum. You can have things that are very K selected, like a chimpanzee, which is going to only have one offspring, maybe two, but that's not common, every 5 years. So chimpanzees don't have a high biotic potential. They're not going to produce a lot of offspring in their life. That's because they're going to do things like breastfeed their young. They're actually going to carry their young around for a long time. I know I've got chimpanzees here in the picture, but another example of that would be something like an orangutan. Orangutans will actually carry their young for almost the first 2 full years of their life. And so when I say carry them, I don't mean that they will never put them down, but when they are moving from place to place in their environment, they will actually carry them for the first 2 years. So when we have a very R-selected species on the opposite end of the spectrum, that would be something like an oyster that's going to have up to 500 million offspring a year. That's not a typo. 500 million, not 500, 500 million. But that's because there is zero parental involvement, none at all. They lay those eggs. Those eggs get fertilized, and they're gone. And they just hope that some survive. But then you can have things here in the middle, like our hare and our frog. So even though they're having a lot more offspring than, say, our chimpanzee over here, and a lot less than our oyster, they don't quite fit perfectly in either category. So you can see our hare here, they're going to provide a decent amount of care to their offspring. They're going to feed them, watch after them, but they can have a lot of offspring at a time, and then they reproduce very quickly after their offspring are born. So that kind of puts them in the middle because they have the parental care side, which tends to be more K selected, but they have a lot of offspring, which gives them a high biotic potential. So that pushes them a little more towards the R selected. And then you have this cute little poison dart frog here. And so it's actually carrying tadpoles on its back. So even though it can have a lot of offspring at a time, it's still going to provide at least some degree of parental care. It may not be the parental care you imagine, like an elephant or a chimpanzee is going to provide to its young, but it's not going to just peace out once they're born like an oyster will. So, what happens with this when we look at invasiveness and disturbances? This is an important thing to consider because it's going to affect those organisms' ability to either survive invasive species or be invasive species, and to be able to either survive or not survive disturbances. So, our K selected, since they have such a low biotic potential, it's hard for them to recover after a disturbance. They just don't produce enough offspring to replace any that were maybe killed off during an environmental disturbance. Whereas our R selected is opposite. Since they have a high biotic potential, they have a much quicker population recovery after some kind of disturbance. When we look at the parental care, so in our K selected, because there are such high levels of parental care, if a parent is killed or dies in some way, that typically is going to also mean death of the offspring. If you have a newborn chimpanzee or elephant and its mother is killed, as sad as it is, they're not going to survive without that parent. But with our R selected, just because there's low parental care, if the parent dies, they're really not doing anything for the offspring anyway, so that doesn't impact them. So it doesn't affect our population size as much. If a parent dies and it's K selected, the offspring also dies. So you're having multiple organisms die because one died. But if one parent dies and it's R selected, its offspring are still able to continue their lives. Now, when it comes to K selective, those invasive species are typically able to outcompete for resources because they have high biotic potential and rapid population growth, so there typically tend to be more of them present in the ecosystem. Sorry, guys. The R selected, though, they're not really impacted by invasive species because they are usually the invasive species themselves because their population can grow so quickly. And so that makes our K selected less likely to adapt and more likely to go extinct, and our R selected less likely to go extinct and have a higher chance of adaptation because they have a larger population and they have a much faster generation time. All right, so our two FRQs for today. The first one is identify one characteristic of an R selected species that could increase the likelihood of the R selected species becoming a more successful invasive species than K selected species. So this is just an identify question, guys. It doesn't say explain or anything like that. So you simply need to state one characteristic that could increase the likelihood of them becoming invasive. And because that is so short, I am going to ask you to do a second one here. So this is looking at zebra mussels versus uninoid mussels and their density per square meter per year. So, what I want you to do is I want you to describe the relationship between zebra mussels and the unionid mussels in their population density in the Hudson River. So, how are those two population densities related to each other? And use data to back that up. You always need to use data, okay? If they give you a data table, cite the data. They're not giving it to you for no reason. So use that to support your answer. All right, and then lastly, on to 3.3, which is survivorship curves. So this is going to keep building on what we just talked about. So the difference in parental care also is going to equal a difference in the amount of offspring that are going to survive infancy and reach adulthood. So in this chart here, you can see that we have time on the x-axis and we have the number of individuals surviving on the y-axis. So you can see that as time is early in an organism's life, if we're looking at type 1 here, there's a very high number of individuals surviving. So our humans are an example here. So most humans are going to survive infancy and childhood. And so you see a very high number of individuals surviving, but once we reach old age, that number rapidly declines. Whereas with our trees over here, that's going to have low survivorship as a seedling. Okay, so they could get stepped on, they could get eaten because there's no parental care if you're a tree. They could be shaded out by larger species, so not very many of them survive to be an adult. But once they reach a certain age range in their life, that mortality rate really levels off and they're able to survive much better. Okay, so the higher up we go is on the y-axis, there's more survivors. And then the further right we go on the x-axis is the older age. Younger age would be over here. So for this, we just need to be able to explain the three survivorship curves. There's type 1, 2, and 3. And then understand that those curves are going to differ for K and R selected species. And for our FRQ, we're going to explain patterns and trends in data to draw conclusions. So when we look at these, the true definition of a survivorship curve is just that it's a line that shows survival rate for a cohort. So when I say a cohort, I mean if we looked at a sample size of 1,000, 1,000 whales, 1,000 squirrels, 1,000 dandelions, they would all be born at the same time. Okay, so they're the same age. So it shows how many of that cohort are going to survive in a population from birth to death. One thing I want you to understand about these is when we have age down here. And so you can notice that age does not have any units on it. And that's because it's a relative number, okay? A dandelion is not going to live as long as a squirrel's not going to live as long as a whale. So it's relative. When we have old age over here, that's old age relative to the type 1 species. When we have old age over here for our squirrel, that's old age relative to the type 2 species. And same thing for the type 3. So understand that this age label isn't concrete. Okay, it's not this is 2 months old, 6 months old, 12 months old. It's not set in units like that. So it's relative to the species that we're looking at that time and their maximum lifespan. So when we look at our type 1, if we have a slower drop in the line, we're going to have a longer average lifespan. So our line stays very stable for quite a while and then drops off at old age. But if we have a faster drop in the line, that means we're going to have a quick die off of our young individuals. So that means they tend to have, on average, a shorter life. So let's look at some characteristics of type 1, 2, and 3 survivorship curves. So type 1 tends to be our K-selected species for the most part. Once again, like I said with our R versus K, it can kind of be a spectrum. So not every K-selected species is going to be type 1, but most of them are. So here we have very high survivorship early in life because of that high parental care. So think of something like a mom grizzly bear. A mom grizzly bear is going to protect her cubs at all costs. She'll fight people. She'll fight predators. She'll fight male grizzly bears. She'll do whatever she can to protect her young. Or that chimp we were talking about earlier, they're going to breastfeed, they're going to carry their young around. So they're providing a lot of care. So we see a lot of those young surviving. So because we have so many young surviving, we still tend to see high survivorship in the middle of the life range. That's because a lot of these species are going to have larger sizes and they're going to be able to defend themselves. So as they reach, childhood or their teenage or young adult years, as we would compare it in humans, they can stand up for themselves. But then what we see is we see a very rapid decrease in survivorship as old age starts to set in. So once we reach a certain age, a lot of the members of that population are going to start to die. So this is going to be most mammals. Then we have type 2, which is really in between R and K. So with that, we see a steady decrease of survivorship throughout life. So think of things like birds and rodents. So there is parental care for their young, but even though they're trying to care for their young, they're little, okay? So they're not capable of protecting their young, or their young may be more sensitive to changing environmental conditions, like think of a baby rat that's born without fur. If we have high temperature changes and it gets really cold, they're not going to be able to survive that because they don't have that fur to insulate them. So they're going to have a constant and steady decline throughout their life. So for a bird, just because it survives its fledgling stage doesn't guarantee it's going to reach sexual maturity. It could still be eaten by a predator, or a number of other things that could still cause it to die in that area between its fledgling stage and its sexual maturity. And then we have our type 3, which those are mostly going to be R selected species. So think of things like insects, fish, plants. So they're going to have very high mortality or low survivorship at a very early stage in life because of that low amount of parental care. Now, I know that sounds bad, but remember that our R selected species are going to have a lot of offspring to make up for this. So it still works because they have so many offspring, they can kind of make up for that high mortality rate because at least some of them will survive. If they have 100 offspring and 75 of them die in their early life, there's still 25 that could reach adulthood. So very few make it to that midlife. So we see a slow, steady decline in survivorship in midlife, and even fewer are going to make it to adulthood. But once we reach adulthood, there's a slow decline in survivorship in old age. We don't reach old age and then see a sudden die off like we do in type 1. And so then our last FRQ here is I want you to take a look at this data that I'm showing you. So you've got age in years on the x-axis, you've got the proportion surviving on the y-axis, and I want you to describe the trend in survivorship shown in this graph. And using that trend, I want you to justify which type of survivorship curve these data represent. So when I say describe the trend, I want you to tell me what is happening over time to the proportion of survivors. Is the proportion of survivors increasing over time? Is it decreasing over time? Is it staying steady over time? And then based on that, tell me which type that represents. And by that, I mean type one, two, or three. Okay.